All right, so let me start the polling. Oops, sorry. All right, so you guys can see the poll question in the polling box. You're given a rod on rails. The rod's moving to the right in that magnetic field. What I would like for you to figure out is the direction of the induced current in that loop. Granted, it only has 3 choices. Okay, got one more who has to decide, and we'll be done. Okay, so we have a distribution of choices in this particular problem. Let me end the poll and share the results. Almost an even distribution. So let me stop the share. And let's go over this. Oops. Let me check my camera. Not sure what happened there. Okay. So we have a rod on a set of rails. And someone asked me the question about the length of the rails. Really, when we do these problems, the L in the equation is basically the distance between these two guys. I always draw a little bit bigger just so you can see that it's a rod that is separate from the rails. The velocity is this way. And the magnetic field is this way. So we can answer this question really 2 ways. First of all, the way we talked about it in class is if this rod is a conductor and it has electrons in it, let's say we have an electron here. What is the force on that electron? Well, the force is going to be, due to the magnetic field, is going to be Q times V of the rod cross B. What is that cross product equal to if those 2 vectors are parallel? Anybody? What's that cross product equal to? What's QV cross B? It's 0. Okay, so that means there's no force on the electron. If there's no force in the electron, you're not going to get any current in the circuit. Now, what's another way to look at it? The area of this loop is getting bigger, right? The object is, this is going to the right. The area is getting bigger. So if we want to calculate this flux, the normal to the loop is perpendicular to the plane. The magnetic field is that way. If you have two vectors perpendicular to each other, what's their dot product? 0. So there's two ways to look at it, and either way will tell you that there's no current induced in this loop. Is there any questions on that? Or are there any questions on that? Sorry. Okay. Next question is the following. Let me blow that up. So you have a wire carrying current I downward, and you have a rectangular loop to the right of it. Which of the three ways, or all of the ways, can you move the rectangle so that there's an induced current in the loop? Which way can you use it? So you can be one of the ways, or it can be all three ways. Okay, everyone has responded already. Okay, so let me show you the responses. So these are the responses. So 4 people choose choice 2 or choice B. Okay. All right, let me stop the share. And let's take a look at this problem. So we have a wire carrying current. By the way, those of you who were in the 12th, the 11th, 10th class, the picture's better now, right? You have current I this way, and you have a loop of wire like this. Which way is the magnetic field through here? Right-hand rule. The magnetic field's out of the board. So everywhere over here, the magnetic field is out of the board. If I move this to the right, does the flux change? If I move it to the right, the field everywhere inside here decreases. So the flux will change. So yeah, I can move it to the right and I will get a changing flux. I'm going to induce a current. What if I move it this way? Which would be choice 2. Remember, this is the integral of b dot n dA. We want to take a look at this. Well, there's a component. Well, the normal to the loop is this way. Right? This thing is moving in this direction. There's a component of the velocity vector that's that way. You're still moving further and further away from this wire. So that means that the flux is changing, which means that you will still have an induced EMF. So 1 and 2 are true. Now, what about number 3? What if I move this loop of wire downward? Well, remember that the magnetic field depends on the horizontal, and the way I've drawn it in the plane here, the magnetic field decreases either to the left or to the right from this point. It doesn't decrease downward. So if I move this downward or upward, this field here is going to stay the same. This field is going to stay the same. This field is going to stay the same. The field here is different from the field here, but if I move this upward or downward, the field will still be the same. The flux will not change. And if there's no change in flux, then there's no induced EMF. So 1 and 2 will produce a change in flux, but 3 will not. So the answer is choice B. Are we okay on that? Yeah, we got to assume the wire's long, yeah. By the way, regarding the picture, I think I was just using too many resources. That's why the picture went bad and the autofocus stopped working. Okay, one more question. This one's a little bit more mathematical because it involves graphs, and that means you have to draw a graph. So we have a current in a loop that varies based on the graph given on the right with the red plot. Question is, what does the induced current in the bottom loop look like? What does the graph of the induced current in the bottom loop look like? You should be drawing a picture to be able to do this one. That's what I would do. I would draw a picture. So I'm going to let you think about this. Remember that the induced EMF depends on the time rate of change of flux. The time rate of change. And I'm saying it based on some of your responses. Wow, I have a nice distribution of answers. Okay, so let me show you the choices. Those are the choices split evenly between choice 2, 3, and 4. Okay. And of course, one group, hopefully, one group will be correct, right? Okay. And I'm not going to draw the loops of wire or anything like that. I'm just going to draw the graph, the graph of the current as a function of time. So, I of t, oops. It decreases linearly for a while, then stays constant for some while, and then it increases like that. Now, that means, well, what happens to the magnetic field? What does the magnetic field look like? So look, when you have a current carrying wire, the magnetic field for a current carrying wire, the magnitude is always proportional to the current. I don't know if you noticed that. Okay. The magnetic field is always proportional to the current. That's always going to be the case. It's going to be a bunch of numbers and then some geometry times I. So however this scales, this will scale the same way. And then so will the derivative. So if B is proportional to I, dB over dt, the magnitude, will also be proportional to di dt. And then you have a nice loop of wire, a fixed area. Okay, then this is going to be proportional to the flux. This will be proportional to the flux because, you know, the flux is the integral of B dot N dA. B doesn't vary with position in this problem. Over the loop because the magnetic field is going to depend on R. So this is also going to be proportional d phi dt. So however this goes, this will go. Why do I want to know that? Because the induced voltage, let me use black. Delta V induced is minus d phi sub b dt. Which is proportional to minus di over dt. With respect to this graph, what does di dt represent? The slope. Okay. So di dt represents the slope at any point, right? But here the slope is constant. Right? Here the slope is constant, and in fact it's minus the slope. So if I plotted minus d phi dt, this slope is constant, but there's a minus sign in front, so I have to get something like this. Here the slope is constant, it's zero actually, because the function doesn't change. I doesn't change as a function of time here. So function does this. And here the current increases at a constant rate as a function of time. Oops, I screwed this up. Sorry. The slope is negative, minus the slope gives me a positive number. Are we okay with that? Okay, and then you'd have a negative here, but the problem is, the problem states that the problem defines our coordinate system. The problem says that the direction of positive current is shown in that problem. Okay. This is what's confusing about the problem, is that it shows us the direction of positive current, which is going to be, when you look at it, the direction of positive current is really the direction of the current shown. So if the current is going, if the current in the bottom coil is in that direction, we've redefined the coordinate system, right? Because which way is the current going to go in that loop? If you look from the top, if you look at the top, the current's going clockwise. Then shouldn't the induced current be clockwise? Okay. Which is opposite the direction of current given. So if I say that this is positive, based on the way they designate positive current in that problem, I'm wrong, right? Correct? My current is clockwise, but the picture says that the current that's counterclockwise is positive. Yeah, let me say it one more time. In the problem, they define the current in the bottom loop to be clockwise, to be positive counterclockwise. Look from the top downward. If you look at the current in the loop, they define positive as counterclockwise. But this current that's induced is clockwise. It has to be from Lenz's law. So based on the way we define the current in the problem, then I have to swap these two. Based on the definition of my coordinate system. Basically, it's like how you're defining what positive and negative is. So realistically, what should happen then is, based on our definition, that's what the graph should look like. Based on our definition. Okay, so this is the graph. It's based. It's based on what we define as positive. Okay. It's based on how we define as positive, because in that problem, they define counterclockwise from the top to be positive. Our current is clockwise as you look at it from the top. Okay. It's tricky. It's a tricky question. Okay, so that's it for my question. So you guys have questions on homework? Any homework questions? You do want to get started on it fairly quickly, because some of them have multiple steps, so multiple parts, so you kind of want to get through the homework assignment. They're not super long problems. The last two are a little bit more longer. My guess is you guys haven't really gotten started on the homework yet. Okay, let me look at number 6. Okay, maybe, and let me call up the problem on WebAssign too, and then I can, it might be hard to see on the screen, but I'll call it up anyway. So we are behind, by the way, we are behind in the class by a week, and we got to figure out a way to catch up somehow. Okay. Let's take a look at number 6. Okay, so we have this loop of wire. Oops. That is strange. Hold on a second. So in part D, you wanted to find the force. Okay. So you calculated the power, and so in part C, you calculated the power, and you got that right. Isn't it true that from Physics 205 that power is force times velocity? That the instantaneous power is force times velocity. So basically you should be able to take the power and divide it by You take the power and just divide it by the velocity. You can also use ILB. Okay, so that's strange. So tell me what you got for the expression for power. What was your expression for the power? So you get NBLV squared so you should get F equals and it marked it as wrong. Did you type it? Oh, you forgot the square in the end? Okay. Other questions? That's fine. Those things happen. The hardest questions on the assignment, I think, are this one and this one. Let me say something about number 15. Okay. Number 15, you have to set up two equations and two unknowns. You got to treat it like a Kirchhoff's law problem. So we have a system like this. Remember, we're dealing with a non-conservative electric field. So there is no such thing as E equals minus the gradient of V. So we have the magnetic field into the board. The left side is twice the area of the right side, so maybe I should exaggerate this a little bit. This is 2A, this is 2A, that's A, that's A, that's A, and that's A. So really the resistance of each side is like rho L over A, rho L over A. Okay, where L are the lengths. And they give you the resistance just per unit of length. So I'm going to write it like this. Some constant times the length, which is going to be 2A or A or some other thing, okay? What I need to do is integrate the induced electric field around a closed loop. I got to integrate the induced electric field around a closed loop. So, and I got to do it for several loops. I'm going to, when I do this, the magnetic field's into the board. I'm going to choose the normal into the plane of the board. So when I do this integration, I'm going to integrate clockwise. So I'm going to choose n hat into board. That means that the integration is clockwise. Okay? And I'm going to choose the electric field in same direction as DL, the direction I'm integrating. If I'm wrong, I'll get a minus sign. So that means that I'm going to choose the electric field to be this way. That means the current is going to be in the same direction as the electric field. So I'm going to call this current I1, and I'm going to call this current I2. This current is going to be I1 plus I2. So the sum of the voltages then, I just got to go around. Basically, I'm integrating this all the way around. Since the magnetic field's constant, the electric field is going to be constant. Let me find my eraser. So I'm going to integrate around in this direction and in this direction. The integral is going to give me my voltage drops. So I'm going to integrate this way. I have here a current of I1 plus I2. The resistance is 2A times whatever that constant is. Over here, I have the same current, I1 plus I2, times K times that length A. And over here, I have the same thing, so I'm just going to multiply this by 2. And then to complete the loop, I have a current I1 here. And then my resistance is going to be K times A. And that's going to be equal to the time rate of change of flux through that loop. Then I do the same thing through this loop. I'm going to integrate clockwise. So here, when I integrate clockwise, I have I2 times a constant times A. And then I go around here, I'm going against the direction of the electric field, meaning that this dot product is going to give you a negative number. And in fact, one thing I forgot these two legs. There's 3 of them. So I'm going to call this d phi B1, d phi, I'm going to call this 1, and I'm going to call this 2, because these areas are different. Then I got to derive the expression for d phi dt here. I derive the expression for d phi dt here. Obviously, this is going to be half of that. Okay, it's pretty obvious because this has half the area. And then you have 2 equations, 2 unknowns. You just solve them. That's all you do. I don't want to solve the whole problem for you, but I'm just setting it up for you. Okay? And then the other problem, which is this one, You kind of want to draw this from a side view. It's really the last part that's hard. Okay, it's really the last part that's hard. So let me draw a nice picture. It's going to slide down the hill. So the current is perpendicular to this plane. This thing is going down. So you have a current coming out either this way or into the board. I'll let you figure that out. And then you have a B pointing downward. As this thing slides down, there's going to be a force that's produced by this. If you do F equals I L cross B, that force has to be perpendicular to both the current and B. That force has to be this way. And this is an induced, this is due to the motional EMF. This is L, and that's the magnetic field. If I rotate my coordinate system, which I usually do for something like this, all right, if I say this is the X direction and this is the Y direction, then this force has two components. It has one component in that direction. So let me go over that again. I apologize for that. I forgot to change the screen. So I drew my picture. Here's my magnetic field. My current is going to come out of the plane of the screen or into the plane of the screen. But the force, the resistive force due to IL cross B has got to be in this direction. Because if it were in this direction, this thing would accelerate. So this is ILB. And because we usually rotate the coordinate system, then this force will have a component along the plane and one perpendicular to the plane. Here's your mg with the x and y components, and then the frictional force is there. But the thing is, in this problem, is that F has, the normal force contributions comes from this and this. Both of these point downward. This angle's theta. Okay, so the normal force is going to be mg cosine theta plus I m lb, and then we're running out of space, sine of theta. Let me write it somewhere else. Let me write it over here. By the way, if you just can tell me by voice instead of chat. Sometimes I don't see the screen. If you can't see the screen, so that I won't keep going. So the normal force, because these two are pointing down, is mg cosine theta plus I motional lb sine of theta. Of course, I'm going to let you figure out what that is. Okay, and then in this direction, you're going to have mg sine of theta minus mu times the normal force equals ma. Okay. Oh, I forgot one term, didn't I? I forgot this term. In the end, you will set A equals 0. Okay? You have to figure out what this is in this problem. So I'm going to leave that up to you, because I don't want to completely solve the problem for you. Is that okay? I apologize if I kind of didn't have you see the board for a while. Does that help a little bit, maybe to get you started on the last two problems? Were you able to see any of the previous problem that I forgot if I had the display not there the whole time. Did you guys see what I drew for this one? Okay, all right, good. Yeah, you might have to just shout it out if you can't see anything, because otherwise with my back towards the screen I can't see what you typed. Okay, so that's all I have then, and I'm hoping that's going to give you enough to be able to solve those two problems. Okay, so I have office hours tomorrow from 1 to 2. So if you have questions, come to office hours. Please get started right away in this assignment. All right, have a good weekend. Okay, so question is, what is the timeline for the test on Monday? I'm sorry, what? It's from 9:30 to 11:30 like usual. Okay. Yeah, I don't want to change the actual time of the test. I'm just going to do it the same way. Okay. All right, have a good weekend. You're welcome.